Hi, we are going to conclude our discussion on work and energy with this lecture. So in this lecture, let us introduce ourselves to springs. Springs are objects which can be stretched or compressed. So naturally, whenever there is a compression or stretching is involved, it means that something is being pulled or pushed, right? That means that there are forces involved. So when you actually stretch or compress a spring by a small amount, the spring exerts a force, right? And that force is called the spring force. It is defined by Hooke's law, named after a scientist, and he studied springs deeply. And the force of the spring, F spring, equal to negative K delta X. Let's study each of these terms. F spring is the force exerted by the spring. This negative indicates that the force exerted by the spring is actually in the opposite direction to the displacement caused when I am stretching or compressing it. If I stretch it, that is, let's say, look at a diagram. If I have a spring and then I stretch it, I would move it to the right. That means the displacement is to the right. The force will be in the opposite direction of this displacement. Alright, so if the displacement is to the right, F exerted by the spring is to the left, and vice versa. If you have a compression in the spring, meaning you're producing a displacement going to the left, the force then would point to the right, the force exerted by the spring. This is all that this minus sign means. K is something known as the spring constant. It is unique to each of the spring that you consider. This variable is a constant, but it has units. It is measured in newtons per meter. It is a constant for that specific material of the spring, but it has a unit that is measured in newtons per meter. Delta X is the displacement of the spring away from its equilibrium or original or natural length. So if I had a spring, this would have been the natural length. Anytime I make a compression or an extension, I am taking it or I am displacing it from its original length. The amount of displacement away from its original length is what this delta X really is. Now let's study some features that are important for the spring force. One of them is that the spring force is not constant. It is not a constant force. What does that have to do with anything? Well, not constant force means that at every instant you're applying a force on the spring to make it stretch or compress. The spring will exert a force which we now know as the spring force. At every instant it will be changing. Every time the spring is stretched or compressed, the force exerted by the spring will be changing. That means the acceleration which will result from this spring force will also not be constant. It will also be changing all the time. That means when acceleration is not constant, we cannot use kinematic equations to describe anything related to springs, because kinematic equations basically only work for constant acceleration. Since the acceleration is not constant for spring forces, we cannot use kinematic equations anymore. The other important feature is that this is the other conservative force that we will learn in this chapter or in this course. Spring force is a conservative force, meaning the work done by this force is independent of the path chosen to go from one point to another. Alright, just like gravity. Every conservative force has a potential energy associated with it, at the energy based on the position. For springs, we call that potential energy spring potential energy, and we will now see a little bit more deeply what this comes out to be. The spring potential energy for springs is defined as the change in spring potential energy delta US equal to 1/2 times K times delta X squared. K is the spring constant of that particular spring. Delta X is again the change in length of the spring, all right, the change in displacement, or the displacement away from the original length of the spring squared. So the potential energy depends on how far you stretch or compress the spring away from its original length with a factor of 2, and K is specific to that particular material for the spring. All right, whenever you have a spring in a problem, you must consider this spring potential energy when you write down your work energy theorem equation. So in general, what we do is to not miss out on any of the energies that we need in our problem. We write down the total potential energy in the problem as the summation of the gravitational potential and the spring potential. So some of the times you may have both of these in one problem, but sometimes you may only need on one. So for example, when there are no springs in the problem, but the object is probably moving in the vertical direction, then you only have gravitational potential energy. But whenever there is a spring involved, say an object moving in the horizontal direction with the help of a spring being stretched and compressed, then you don't have a gravitational potential energy, but you have a spring potential energy. When you have the object moving in the y direction with a spring attached to the object, then you have the stretching and compressing of the spring, and also the spring is making the object move in the vertical direction. So you have both gravitational potential energy and spring potential energy. So this is a general rule which changes based on the problem. So in general, the total potential energy for any problem is the summation of gravitational and spring. All right, then let's look at a problem. Let's look at what we have learned so far. Let's investigate our learning by looking at this problem where we have a mass of 480 grams attached to the end of a spring, and the other end is attached to the ceiling. This mass makes the spring stretch. All right, so as it stretches and comes to a final resting point, we measure the new length of this new spring or stretched spring to be 20 centimeters, and the original length of the spring was 10 centimeters. So we want to find out what is the spring constant for this particular spring. So spring constant is related to both potential energy and forces. However, this would be easier for us to work with forces. Why? Well, we can check by just drawing our free body force diagram. First of all, let us draw our free body force diagram. Let's choose the y-axis upwards to be positive, and there is no need for an x-axis. So on the block, what are the forces? This must have a weight since it has a mass, and the spring exerts a force on it, the spring force, F spring. All right, and let's say in this position the box is at rest after the spring has stretched to its new length, 20 centimeters. So this is a point of rest, so we don't need to worry about acceleration. Since acceleration is 0, we can write down Newton's second law and not worry about the changing acceleration. Okay, what does Newton's second law tell us? But before that, 480 grams is equal to 480 over 1000 for kilograms, so we get 0.48 kilograms to work in meters, and 10 centimeters is 0.1 meters, 20 centimeters is 0.2 meters. So we have changed everything to SI units. Now we are free to write down Newton's second law in the y direction. The y direction, we have Fy equals to MAy. Ay is 0, so on this side it is all 0. What are the forces involved? We have the F spring in the positive direction, let's call it Fs, and then we have the weight in the negative direction, so negative mg, equal to 0. So Fs is equal to mg. Now what was Fs? Fs we learned was the vector equation was negative k delta x. Well, this was a vector equation, and remember Fs was the force exerted by the spring. So Fs and delta x was both for the spring. However, now we are looking at the block, and the spring exerts a force on the block which is in the upward positive y direction as chosen. So for this choice of coordinate axis, we don't actually care about the minus sign because we have already taken care of it with our coordinate axis. So we can just use the magnitude of this force, alright, because that is what Newton's second law does. We take care of the directions using our chosen axis with our plus and minuses, and then we put in the separate magnitudes of the force, alright, with the signs up in front of them. For this problem, Fs is upward, it's positive, so Fs, the magnitude, is just k delta x equal to mg. What is delta x? Delta x is the change in displacement of the spring from its original length. Its original length was 10 centimeters. Its new length is 20 centimeters. So how much did it stretch? It stretched by 10 centimeters, right? 20 minus 10. So this delta x is nothing but 0.1 meters. So k is in fact, m is 0.48 times g is 9.8 divided by delta x is 0.1. This comes out to be around 47 newtons per meter. This is the spring constant for this particular spring. So far we have talked about energy being transferred over a distance, or the work done over a distance. When a force makes something move a particular distance, we say that work is being done over that distance. Over that distance, the same thing would be an energy was transferred from me to say that object that I was moving. We can also say that we can also make a statement like I was moving boxes all day. So you were doing work all day. All day was or is a time frame. So when you're comparing the work done over a period of time, we are then introducing what we know as power. Power is the rate of energy transfer, or energy transferred over a period of time. And we know that energy transfer is the same as the work being done. How does energy transfer from one form to another, or from one object to another? By work. When a work is done by one object on the other, then an energy is transferred. So we can define power with an equation that looks like P for power equal to the work done over the time taken, or the time interval of the work. Alright, so the work done is the same as the total energy transferred during this period of time, and the unit for power is SI unit. SI unit is watt, after James Watt, the steam engine guy, and it is capital W is the symbol for watt. Let's test our understanding by looking at an example. We have a sports car that goes from 0 to 62 miles per hour, which is around 27.7 meters per second in SI units, in 3 seconds. So it makes 0 to 62 in 3 seconds. Now the mass of the car is 1550 kilograms. We want to know the power that the engine provides to the car. Alright, so it's pretty straightforward if we can set up an equation like this. The first thing we want to do is to find what this work is. We know this work is the change in energy, and we are ignoring friction for this particular question. So let's think about our work energy theorem. Our work energy theorem tells us that work non-conservative is equal to the change in kinetic energy plus the change in potential energy. Now the potential energies that we have looked at so far, and that those are the only two potential energies that we will look at in this course, was gravitational potential energy and spring potential energy. None of those are involved in this problem. There are no springs, so spring potential energy is 0, and the car is moving horizontally. Whenever things are moving horizontally, that is, the position is changing of the object horizontally in the x-axis, there is no gravitational potential energy, because for there to be gravitational potential energy, you need to be working against gravity in the y direction. So the potential energy in this problem is simply 0. So makes our life easier. Now we know that the net work is nothing but the total change in energy, and in this case the only energy involved is delta K. The net work is a combination of whatever work you have done by non-conservative forces like friction added to any other forces that are not friction, right? So that is the total work done by kinetic energy here. So what is the change in kinetic energy? Change in kinetic energy is, as we have met long time ago now, 1/2 times m Vf squared minus Vi squared. Since kinetic energy is nothing but 1/2 mass times velocity squared. To find change, kinetic energy is this. To find change, we have to include a final point and an initial point. Okay, this is what this looks like. Vi was, it started from 0, so it's 0. Vf is 62 miles an hour, which is 27.7 meters per second. So kinetic energy change is 1/2. Mass was 1550 times 27.7 squared. This comes out to be around 441192 joules. This is the total kinetic energy provided by the engine. This is equal to the work done by the engine, the net work done by the engine. So power is nothing but this work done over the period of time we are talking about. The period of time is 3 seconds, and so we just take this work for 1192, divide that by 3. This gives us the power in watts, which comes out to be 147064 watts. But we commonly know the power of engines of cars or vehicles given to us as horsepowers. Horsepower is another unit for power used only for vehicular and machines like tractors and so on and so forth. 1 horsepower is equal to around 740 watts, I think. It's equal to 746 watts, 1 horsepower HP. So if you convert that, how do you convert so horsepower is actually a bigger unit than watt. So to go from watt to horsepower, you have to divide this by 746. So the power is in horsepower is power in watts divided by 746. This gives you a horsepower of 197 HP. This is the horsepower that the engine needs to have to produce this kind of acceleration.